Alright, so this is going to be video 2 for the light unit. Looking again at the colors of the rainbow, you may notice that some of the colors are missing. Magenta, cyan, white is missing also, but remember white is a mixture of everything. It turns out that certain colors, brown, magenta, cyan, it turns out that none of those colors are actually pure colors. They're mixtures. So many animals do not sense color the way we humans do. They can only simply see something as brighter or dimmer. So humans, we have 4 kinds of sensors in our eyes. So 4 sensors. One sensor is the rod, and rods sense brightness, how bright something is, and we find these in most animals. And then we have cones. There's actually 3 cones. There's a red, green, and blue cone. So that makes up our 4 sensors. So we got rod, red cone, green cone, blue cone. And this graph right here shows what these cones can detect. So down here we have our color spectrum, Roy G. Biv. And the first thing you may notice is that the red cone, it has its maximum sensitivity in the green spectrum, not red. So what happens is that the eye gets signals from both the red cone and the green cone. So if the signal from the green cone is stronger, we see green. If it's not, we see something else. So to call a signal red, the signal from the red cone needs to be twice as strong as the signal from the green cone. All of the colors we can see are a result of the different signal strengths from these 3 cones. You may also notice that the red cone, it can also see blue. The red cone kind of covers a little bit of everything. The green cone, now it's truly, its maximum sensitivity is in green, but it can see a little bit in the red, it can see into the blue. The blue cone, it cannot detect red at all. And really the blue cone can't really tell red or green. And that's going to come up later, so keep that in mind. But here we see the sensitivities and what each cone is sensitive to. So about 5% of all males, about 0.5% of females, are colorblind. That means that they do not have both red and green sensors, or red and green cones. Maybe they have less sensitivity. Maybe one of those cones doesn't work as well as it should. So if we take a look at this, going back to this graph here, if you're missing, let's say if you're missing the red cone, you only have blue and green, you would have trouble seeing red. Or if you're missing the green cone, if you only had the red cone, you might have trouble telling the difference in some of these colors. So, people with color blindness, the most common is that they cannot distinguish red from green. And that's because with just 2 sensors, the blue cone and the green cone, or the blue cone and the red cone, light in that green-red region is not detected by that blue cone. So with only 1 signal, or not a ratio, the brain simply cannot guess what frequency the light is. That leads us to this test right here. This is a color blindness test. People, if you when you look at the left side of this, like we see 25, 29, 45, 56, 6, 8. We see these we can see these. Somebody who has some color blindness would only be able to see the 25 and the 56. So basically, it's a way of testing to see if you have some color blindness. Kind of moving on with the color stuff here. Let's talk about a rose. Roses do not emit light. They reflect light. So if we pass sunlight through a prism and then place a deep red rose in various parts of the spectrum, the rose will appear brown or black in all parts of that spectrum except the red part. In the red part of the spectrum, the petals will appear red, but the green stem and the leaves will appear black. So this shows that the red rose has the ability to reflect red light, but it cannot reflect other kinds of light. The green leaves have the ability to reflect green light, but they absorb all the rest of it. So when a rose is held in white light, remember white is a combination of everything, you know, the petals appear red and the leaves green. That's because the petals are reflecting red light while absorbing everything else, and the green parts are, reflecting green light but absorbing everything else. So usually a material will absorb some frequencies of light and reflect the rest. So if a material absorbs most visible frequencies and reflects red, it looks red. If it reflects all visible frequencies, then it'll look it'll be the same color as the light that shines on it. If a material absorbs all of the light that shines on it, reflects nothing back, then it's going to look black. So an object can only reflect frequencies that are present in the illuminating light. The appearance of a colored object depends on the kind of light used. So this kind of gets into photography a little bit here. So if you got a candle flame, the candle flame emits light that is deficient in blue. There's not a lot of blue light in a candle flame. Its light is yellowish. An incandescent lamp, so that's the light bulb with the tungsten filament in it. It has light that is richer towards the lower frequencies, so enhancing the reds. And a fabric with a little bit of red in it, the red will be more apparent under an incandescent lamp than when it's like lit up by a fluorescent lamp. Fluorescent lamps are richer in the higher frequencies, so blues are enhanced under them. So if you're thinking about photography, if you really want your reds to stand out, you want to take your picture with incandescent bulbs. If you want the blues to stand out, you need to use a fluorescent light. So with various types of illumination, it can be difficult to tell the true color of an object. Colors appear different in daylight than they appear when illuminated by either kind of lamp. So that's also something to kind of think about when you're doing interior design. When you're choosing the paint for your walls, you want to think about what kind of light you're using. We also have the selective transmission. This is like your filters here. So the color of a transparent material depends on the color of light it transmits. So a red piece of glass looks red because it absorbs everything except for red light. Lets red light through. The piece of glass that contains dyes or pigments, fine particles that selectively absorb certain frequencies and selectively transmit others. So from an atomic point of view, the electrons in the pigment molecules are set into vibration by the illuminating light. Some of the frequencies are absorbed by the pigments, others are re-emitted by from the molecules. The energy of the absorbed frequency increases the kinetic energy, so the glass kind of gets a little hotter. Ordinary window glass is colorless because it transmits all visible frequencies equally well. Okay, I think that's going to be good for this second video. In the third video, we'll finish up this unit. We'll talk about how light is mixed, and we'll talk about sunsets and sunrises and things like that.